Module 7, Lesson 1, Transformation in R. In the previous module, we learned that one of the data exploration technique is to draw simple graphs to understand patterns in the underlying data. Simple graphs like histogram, density plots, scatter plots, box and whisker plots are used to study the univariate and bivariate as well as multivariate distribution. Scatter plot or box plots can be used to get feel of distribution of numeric variable per category as well as can be used for comparison between numeric variables. Pie diagram and bar plot are used to understand the distribution of the categorical data. At the end of this lesson, you will understand what do you mean by transformations, why the transformations are needed, and also learn different transformation techniques. Introduction to data transformation. During data exploration, one may identify need to transform variables. Normality is desired for most of the studies as first assumption to proceed further. If the data is skewed or equally distributed, it's better to transform it to make it as normal as possible. Transformation is the replacement of a variable by a function of that variable. For an example, x can be rewritten x is equal to log of x or x is equal to square root of x. In a stronger sense, a transformation is a replacement that changes the shape of a distribution or relationship. Let's look at some useful transformations. The most useful transformation in introductory data analysis are the reciprocal, logarithm, cube root, square root, and square. It often helps to transform and see the results. Often it helps to transform results back again using the reverse or inverse transformation. Let's see some examples. So if you are doing a transformation as a reciprocal, then the inverse transformation would be again taking the reciprocal of the result. For an example, if t is equal to 1 upon x, the inverse transformation would be 1 upon t, which is going to be the value of x. These are some of the other transformations on the similar lines. Typically, if the values are large and spaced, we shrink them using shrink functions like square root, cube roots, or logs. Now let's consider a dataset from MAS package. MAS is a modern applied statistics with S. MAS supports functions and datasets. We will explore variables from this dataset and decide if any of the variable needs transformation depending on the current distribution of that variable. Our aim is to make the skewed variable symmetric. Now let's install and load the MAS package. If you have already installed the package, then you just need to run the library command to load the package. Otherwise, install the package using install.packages MAS and load it using library MAS. Once you are done with the loading the MAS package, now let's load the data which is there in a MAS package. So load the data NL schools by using a command data NL schools, and then let us attach the data NL schools using attach NL schools command. We usually prefer to attach the data so that the variables can be used freely in any calculations. Let's first understand the data NL schools. This dataset is given for 8th grade pupils in the Netherlands. The data frame contains 2,287 rows and following columns. Lang is referred for language test score. IQ is verbal IQ, whereas class tells you about the class ID. GS class size variable denotes the number of 8th grade pupils recorded in the class. There may be others also. You can look at the comp variable, and some may have been omitted with missing values. SES variable denotes the social economic status of pupils' family. COMB or COMB denotes where the pupils taught in a multi-grade class, 0 or 1. Classes which contain pupils from grade 7 and 8 are coded 1, but here only 8th graders were tested. Let's look at the summary of NL schools. We can see that we have Lang, IQ, GS and ACS are numeric variables. So we get to know the summary statistics for these 4 variables. Whereas class and COM are categorical variable. COM is a binary variable, so we have a frequency or count for 0 occurrences and 1 occurrences. 0 occurs 1658 times, whereas 1 occurs 629 times. Whereas for a class variable, these are the frequencies for the class IDs, which denotes how many pupils were there in that particular class. Now let's start exploring SES column. For simplicity, we are going to explore SES column only, as we have already done the exploration beforehand. When you get a new data, you must explore all the variables and then decide on which variable you would really need to do the transformation. Here, we have done this study beforehand. So we will stick to SES variable, which is a socio-economic status of a student. Now let's explore SES variable by looking at the histogram. Let's look at the histogram. The histogram tells that it's not normal, whereas it looks positively skewed data. Let's confirm this. To get the skewness of a variable, we must install and use the moments package. So let's install a moments package using install.packages command. Then let's load the package using library command. Let's use the skewness function on SES. The skewness is 0.4052221. This shows that it is little positive skewed, which we just confirmed from the histogram too. Well, what is a positive skewed data? Positive or right skewed data is where you have lot of data at left and it is wrong at right, which means in this case we have more data at the left side of the graph. We can see that this initial portion at the left hand side denotes that the frequency of data is about 200 or so for data points between 10 to 30. Whereas as you go towards the right, there are less data points. This data is clearly right skewed. It is wrong at right because most of the data points are at the left. What about the kurtosis of the data? The kurtosis of the data or a shape of this data denotes that it is not normal or mesokurtic. Normal data typically has kurtosis of about 3, whereas the skewness of the data should be 0 or around 0 if it is a normal data. In this case, since it is positive skewed, the value is more than 0. Had it been the value less than 0, it would have been a left skewed or negatively skewed data. We must do some transformations to this data to understand how it looks like, or to make it more normal or symmetric. Let's try roots, logarithm and reciprocals. Let's start with natural log. Before that, let's look at the actual values of SES, maybe some top 6 values, which looks like 23, 10, 15, 23, 10, 10. Now let's look at the log values of these corresponding ACS values, which looks like 3.135, 2.30, 2.70 and so on. So we have basically shrunk those values. Now let's look at the skewness of this log transformation. That is negative. It is minus 0.3675, which means now the data has become left or negatively skewed. Let's look at the kurtosis. It is 2.58, so it is still not really near to 3. Let's look at the histogram of this log transformation. We can confirm that it is indeed a negatively skewed data now after this transformation. Also, it does not appear at all like a normal or symmetric data. Let's try reciprocal transformation. Now by doing a reciprocal, that is 1 upon SES, the values have further shrunk to 0.043, 0.100, 0.0666 and so on. The reciprocal transformation has made the skewness worse, and it is now positively skewed at more than 1 point and more than 1, which is around 1.38. Whereas the kurtosis is 4.84, has increased. The histogram of 1 upon ACS tells you that it's indeed not a good idea to choose reciprocal transformation. Now let's try square root. When you do the square root of ACS, the values are shrunk, but they are not shrunk as before. So now the values are 4.79, 3.16, 3.87 and so on. The skewness is 0.05160,334, which looks good. Kurtosis of the square root transformation is about 2.22. Not great, but still okay because it is near to 3. The histogram suggests that it looks better. The graph is better than just using the SES variable as it is. It looks nearly normal, though not exactly normal distribution. Now let's put a star mark to this. Now let's remember this transformation and let's explore if there is any other transformation which can be better than this. Let's try the reciprocal of square root. Reciprocal of square root would further shrink the values. The skewness is now 0.85 and the kurtosis is 3.45. The kurtosis wise, it looks fine with the number. Let's look at the histogram. Well, it has not really added good to the skewness. So let's explore any other transformation is there which could be better than this. Let's try cube root. Since so far square root was a better option, now let's try the cube root option. Cube root has shrunk the values. The skewness is now negative, though it is slight negative. The kurtosis is 2.29. Well, the values are not really better. Let's see if any other transformation could help us. Let's try the sine function. Sine function would further shrink the values and also we get some negative values over here. Well, skewness is 0.03, good by number. Kurtosis 1.29, gone for a toss. Let's look at the histogram. Histogram tells that this transformation is not good at all because it is not really that symmetric or mesokurtic or normal distribution way. In fact, the values are scattered and are away from the mean and the median values. Let's look at the exponential transformation. Exponential transformation would further shrink the values. Skewness, very bad, to 3.82, whereas kurtosis has gone for a toss, it is 15.70. It is worse. So let's go back and check which of the transformation was better so far. Exponential transformation, not a good idea at all. Let's summarize. We understand that square root function has made little better in terms of normal distribution. Out of all these transformations, sine and exponential was a bad idea because they have shrunk the values as well as has scattered the values away from mean. Whereas natural log and cube root where the negatively skewed transformation as well as reciprocal has transformed it to a positively skewed transformation. So we can conclude that square root is a good bet. Let's go further with the square root transformation. So we have seen this transformation. Now we will like to add a variable in our data frame NL schools, and so let's add it. Usually we would not delete the previous variable, but we would certainly add the new variable in our data. It looks good so far. So we would preserve our original values as well as the new values. To do that, to combine the data, we would use cbind function or a column bind function to bind the new column into our NL schools data. Now this data is ready for the further analysis. There are three ways for choosing the Bethe transformation. You look at the skewness. If the skewness value is near to 0, then we conclude that the data is almost normal. We look at the kurtosis, and if the value is exactly or near to 3, then we conclude that the data is normal or mesokurtic. The visual inspection by looking at the histogram tells you about the symmetric bell-shaped distribution, which helps us to understand whether the data would be normal or not. So we just learned about transforming the data. Now let's check your knowledge on this. Well, let's wrap up. We just learned that normality is desired for most of the studies as first assumption to proceed further. If the data is skewed or equally distributed, it's better to transform it to make it as normal as possible. We also learned that certain techniques of transforming and checking for normality of the data. Finally, we learned to incorporate the transformed column in our data for further analysis. Thank you for listening.